Hello, my name is Max Starseski. I've been your grader for this semester. I understand you have an exam coming up this Thursday, so I figured I'd record me working some problems I thought might be helpful for your reviewing. This is the first problem I came up with. I've got a 12-volt source here and a network of resistors here. We're given all the resistors except for this one here, which we have to calculate. We're given current through this branch, this 4-ohm resistor here, which is half an amp. So the first step that I took was to do KVL around this loop, call that loop 1. Loop 1. And that would be 6 times 6, 2 times 2, 0. Right, you can see wheeling of these two resistors here. We call this IR6. If we call this IR2 in this direction, it will be in opposite direction, so they cancel out like this. So if we solve for IR2, 6 R2 equals 7 amp times 4 ohms, which is just the same thing, half an amp. If we do KCL up here, call that node 1, you can see we have both these currents. We can actually just get this current here, call that IR1. Do that over here. L node 1. We would get I1 equals 2 6, which is just half an amp plus half an amp, just 1 amp. Next, we can do KVL around the outer loop here, like a don't full loop, but I think you get the idea. Call that loop 2. Loop 2. That would look like this. 12. 6, 6, 6. Sorry if my handwriting's not great. I'm not used to drawing on a chalkboard. Minus 4 times 4 equals 0. So, our 12-volt source, we have R1 times IR1 voltage across this resistor, IR6 times R6, IR4 times R4, call IR4 this IR4, R4. So you can see we have everything in here except for IR4, so we're going to solve for that. Minus I1 6 all over R4 6. And so that 12 1 amp 4 ohm minus half an amp times 4 ohms all over 6. And that's 1.5 amps. So we have this current, we have this current going down through here, we have this current. You can see there's no resistor here, so these two nodes, this node and this node down here, are basically the same node. So we can get the current going through R3 by just doing KCL here. So I'm going to just erase this so I have space. We'll call that node 2. Let's see. Hopefully you can see this. Now 2. You would get I3 I4 equals I2 I6. Solve for IR3. I have 3. Tremendously bad 3. IR3 equals I2 minus IR4 plus IR6. Let me see if I can just squeeze this in down here. That equals half an amp minus 1.5 amps plus half an amp. And that equals minus 0.5 amps. So we have this current, we have this current. We can get this current by doing KVL around this loop. I have to draw pretty small here. Call that loop 3. I'll have to erase something here. Space. So now 3. You would get IR4 times R4 minus IR3 times R3 minus IR5 times R5. That'll equal 0. Alright. You only have those 3 resistors. So solve for IR5. R5 that's IR4 4 minus IR3 times R3 all over R5. That is 1.5 amps times 6 ohms. Minus negative 0.5 amps. times 4 ohms, all over 14 ohms. And that equals 0.7857 amps. You can see it. Put it across 2 lines, you don't quite have enough space. So, we have the current going through this resistor, I5, pretend that's a 5. We have IR5, we have IR3 going this way, we can get the current going through RA, just using KCL right here. If I erase this again, so like that. KCL, call this about 3. Call this IRA. You would get IRA plus IR3 equals IR5. So for IRA, and that equals 1.2857. Okay, so we have the current going through this resistor. If we get the voltage going across it, then we can very easily get the resistances. So we can just do KVL. Do KVL over here. Call that loop. I guess we're up to 4 now. 4. R5 minus 12 volts, 0. So in my solution, I didn't actually get the voltage, I just solved for RA in this. So you'd get RA equals, let's see, 12 volts minus R5 R5 right over RA, IRA. That equals times 14 over 1.2857. That'd be amps. These would be amps. That'd be ohms. These are volts. And you would get 0.7779 ohms. Okay, so this is the second problem I came up with. We have this resistive network here, with plus 5 volts up here, negative 5 volts down here. Part A asks us to find the equivalent resistance between these two sources, and part B asks us to find the current through the 3 kilo ohm resistor, this one right here. So, let's start with part A. I did this, I started with something called a delta to Y conversion. I'm not sure if you guys have covered that, but basically you take this piece of the circuit here, you redraw it like this. So okay, 1K and 2K. Right, you can see there's only 3 resistors here. We can draw this sort of triangular configuration. And a delta to Y conversion is where we convert this to resistors, 3 resistors arranged like this. So you'll have plus R3, R2, R1. Copied these formulas from the book. So R1 equals, if we call this RA, call this RB, and call this RC, then R1 equals RB times RC, RB times RC, all over RA plus RB plus RC plus RB plus RC. Right, and you can sort of see how this would end up being for the other resistors, right? R1 is this one, and we summed these 2 resistors, right? So you'll see with R2, we'll end up summing these 2 resistors. With R3, we'll multiply the resistors, not sum them, right? We've got the sum of all the resistors here on the bottom, the sum of the 2 adjacent resistors there on top. So R1, that would be 2 kilo ohms, 1 kilo ohm over 1, 2, 5 kilo ohms. That would be 0.25 kilo ohms. So for R2, you can see it would be sum of all these 3's 8. It would just be 5K times 1K over the sum of all of them, 8K. That is 0.625. 3 is, let's see, R3, 2K times 5K, just do 10 over 8, 1.25K. So we can redraw the circuit. I should have put this somewhere else. I guess I can squeeze this in down here. So we redraw the circuit. We would have plus 5 volts. Resistor here. 3 resistors on the side. Minus 5 volts down here. This is 1.25K. This is also 1.25K. This is 0.625K. This is 3K. This is 0.25K. This is 0.252K. And this is 2K. I'm sorry if you hear some clattering noise in the background. I'm in a really large garage with some big metal doors and it's kind of weird. So you can see we did this delta to Y conversion. I did this one too. I skipped that step because you can see these resistors are the same. You've got a kind of a symmetry there, so we can just do both of them. And then it's just as simple as combining resistors in series and parallel. So we would have 1.25K. That's in series with this combination, so 0.25 plus 2 plus 0.25. That's in parallel with 0.625 plus 3 plus 0.625. In series with this 1.25 on the bottom here. 5. Plug that all into your calculator. You would get the equivalent resistance is 4.074 kiloohms. So that's part A. For part B, finding the current through the 3 kiloohm. There's 2 ways you could do this. With these delta to Y conversions, the currents in this circuit here are different, but outside of it, it's all exactly the same. So the current going through the 3 kiloohm in this circuit is the current going through the 3 kiloohm in this circuit. You can see with this one, it's going to be a lot more complicated getting that current. With this one, it's basically just, you know, a current divider. We have the equivalent resistance. We can figure out what the current is going through this network and just do current division to get this current. I'm not going to do that. I'm going to do the harder one. Yeah. And solve it using mesh analysis. So, with my mesh analysis, I called this loop 1, this one loop 2, this one loop 3, and I did a split source configuration here. Not quite sure if you guys have seen that before, but basically what this is, if you just consider this whole resistor network here one resistor, then this 5 volts negative 5 volts, that's the same as this actually, I think I might have drawn that backwards. Plus, minus 5 volts. I'll make it so that they add. So, 10, they should be in the same direction. No, it should be opposite directions. I believe it's the same as that. Basically, we're just sort of grounding it in the middle of this source here, right? If we want to reference it differently, we could say that it's the same as this 10 volts. We would just have a different reference voltage, which makes no difference here because we're finding current. But anyway, the reason I explain this to you is because you can see that creates one more loop in the circuit. So loop 4 is going from the plus 5 volts to the negative 5 volts. Okay. So our equation for loop 1 is going to be 5 times I1 plus 1 times 1, 2, and let's use a normal convention here where the current in the first loop is I1, current second loop I2, so on. Plus 2 times I1 minus I4. That'll equal 0. Alright, those are all the voltages in that loop. We'll simplify this. 8 I1 minus I2 minus 0 I3 minus 2 I4 equals 0. You may wonder why I have this 0 I3 here. It's because I'm going to end up turning this whole thing into a matrix and plugging it into my calculator later. It's nice to have that 0 I3 there to remind me to put a 0 there in my matrix. And I simplified this all in one step. It's really easy to mess these up, so you might want to do some intermediate steps in yours. You know, you could forget a sign here and make this a plus. All kinds of easy mistakes to make. Okay, so our second loop, we would have 1 times I1 minus I2 plus 3 times I2 plus 1 times I2 minus I3 plus 2, running out of space, I2 minus I4, 2 minus I4, that's 2, and that all equals 0. So we can simplify that. Minus I1 plus 7 I2 plus minus I3 minus 2 I4 equals 0. Okay. Loop 3. One times I3, that is 3 minus I2 plus 5 times I3 plus 2 times I3 minus I4. I2. 2 times I3 minus 2 times I3 4. Yeah, that looks right. We can simplify that. 0 I1, putting that placeholder in again to remind me to put a 0 in there when I put this in matrix form. I2 plus 8 I3 3 minus 2 4 equals 0. Could divide out a common factor. Well, no, 1 I2. Can't divide out. I guess we'll put 4 down here. 4, so minus 5 volts plus 2 times I4 minus I1 plus 2 times I4 minus I2 plus 2 times I4 minus I3. 2 I4 minus I3. And so we can simplify that. Hopefully you can see that. You can't see it. Okay. Let's see. We minus 2 I1 minus 2 I2 minus 2 I3 plus 6 I4 equals 10. Let's see. We can actually simplify this one step further. Divide out a common factor. Minus I1 minus I2. Really hard to draw right on the bottom of the board. Minus I3 plus 3 I4 equals 5. Always remember to divide out the factor from both sides. Okay. We can turn that into a big matrix. Got just enough space over here to draw a matrix. So, take this simplified first equation here. 8 8 minus 1, I'll just read it off of here. 0, minus 2, 0. Do the second equation, minus 1, 7, minus 1, minus 2, 0, 0, minus 1, 8, minus 2, 0, minus 1, minus 1, minus 1, 3, and 5. Okay. You could put this into reduced row echelon form by hand. That would certainly be neat, but I would be inclined to make mistakes if I did that. If you have some more advanced calculator like a TI-84, it can reduce this matrix. MATLAB can reduce this matrix, but you won't have MATLAB on your exam, so that's not very helpful for you. If you put this into reduced row echelon form through whatever means, you get both. Need to make myself some space. I'm running out of chalk. So reduce this. You get 1, 0, 8 over 0, 1. 10 over 11. 0, 1. 8 over 11. 0, 0, 1. Sorry, they're kind of offset. I have a hard time drawing it. It's really small. 27 over 11. And we know, the way we set this up, I'm just going to draw along the top here. I1, I2, it's a 2, I3, and I4, right? So I4 equals this, I3 equals this, I2 equals this, I1 equals this. As a quick sanity check, you can see, I mentioned this earlier, this circuit's symmetrical sort of across this axis. So we know the current going through here should be the same as the current going through here due to that symmetry. And it is, right? I1 is the same as I3, 8 over 11. We set out to find the current through the 3 kilo ohm resistor, right? That's going to be I2. So that is going to be this value. I2 equals 0.91 milliamps, right? It's milliamps because I didn't draw the K's on all these when I was setting up these equations, but they're all kilo ohms. Our voltages are volts, so volts divided by kilo ohms is going to be milliamps. Yep. And I checked this with the simulator, so I know it's right. Okay, so this is the third and final problem I came up with. You have this network here, bunch of resistors, got a 12 volt source here, 1 amp source here, we're referenced here, and we want to find V0 or V out here across this 60 ohm resistor. So I did this using nodal analysis. Call this node A, call this node B, and I called this node C. Blown all across this. So, in this circuit, we have something, I'm not sure if you've covered this yet, something called a supernode. It's when you have a source between two of your nodes, right? So, with this supernode, we can pretend that, we can write one equation where we pretend that A and B are just one node. And then we have another equation where we just say that VA minus VB is 12 volts, right? Because we have 12 volts source here. Of course, the voltage between them is 12 volts. So, start with that first equation. VA minus VB is 12 volts, right? So, yeah, pretty straightforward there. And then with the supernode, just pretend they're one node, and yeah, treat them as such. So VA over 60 plus VB over 120 plus VB minus VC over 30. Okay. So multiply this whole thing by a common factor of 120, and you get, or yeah, sure, 2VA plus VB plus 4VB minus 4C equals 0. Simplify that, get 2VA plus 5VB minus 4VC. 4VC equals 0. All right. So we have that equation. We can do nodal analysis at node C here. I'll do that here. C VC minus VB over 30 plus VC over 90 minus 1 equals 0. Minus 1 comes from this 1 amp source. With the way we're doing nodal analysis, you know, VC, if you have positive to negative, then VC over 90 would be a current going downwards out of the node. VC minus VB over 30 would be a current also going out of the node. 1 amp is of course a current going into the node, so it has a different sign. We could of course write these all as an opposite, with the opposite sign, but yeah, whatever floats your boat. So that would be simplified to 4VC minus 3V VB equals 90. Right, we get that from multiplying the whole thing by 90. You gotta remember to multiply this 1 by 92, or completely messed up in the end. I add this 0VA to mine, because I'm also gonna solve this one as a matrix. So 0VA minus 3VB plus 4VC equals 90. Right. Yeah. So, just like the last problem, we can very easily turn this system of equations into a matrix. So, 1, -1, 0, 12. That comes from that first equation I wrote there. I didn't have the VC in there, but I think you know it's 0. 2, 5, 4, 0, 0, -3, 4, 90. So again, you could reduce this by hand. It would be easier than the last problem because it's only a 3 by 3. I'm not going to, but you certainly could. So that turns into 1. Let's see. So it's 28.5. 16.5 and 38.875. And again, like the last problem, with the way we define these, this first column is VA, the second column is VB, and this third column is VC. You can see from the way we've defined our nodes, VA and Vout are the same thing. So you just take this, VA equals Vout, Vout equals 28.5 volts. That's all I had prepared. I hope these were helpful to you. If you'd like me to record more of these, let me know before like Wednesday, and I might be able to record another, especially if you give me problems to work. That makes it a lot easier. I could probably like buy markers or maybe even write on a tablet. I have a tablet, but I hate writing on a tablet. But yeah, if you found this helpful, let me know. I could certainly make more of them. Have a great day. Good luck with the test. Bye-bye.